important thing to think about logic is that the truth or falsity of a compound proposition, such as P or Q, does not depend on what the propositions P and Q actually are, but only on whether they're true or false. In other words, what I mean is this: supposing that P is a true proposition, then it doesn't matter whether it's the true proposition 2 plus 2 equals 4, or the true proposition there are 29 days in February in a leap year, or any other truth proposition. It doesn't matter specifically what it is, it only matters that it's true. Similarly, suppose Q, for example, is false. It doesn't matter whether it's the false proposition 2 plus 3 equals 7, or whether it's the false proposition there are 31 days in February. It doesn't matter. It only matters that it's false. And therefore, the main thing that we want to do is the following. Or at least the first thing, perhaps would be better to say. The first thing to do is the following. Given truth values, T or F, true or false, for propositions P, Q, R, etc., determine the truth value of a given compound proposition. And it's really just like doing algebra. If you have some calculation to do involving addition, subtraction, multiplication, division, you just do it step by step. You do one calculation, then you tack on the next calculation, then you tack on the next calculation, and so on. And you do the same thing. What we need to do for a start then is know what are the basic values for and, not, or, etc., things like that. Very easy one for a start, negation. Truth value of not P is the opposite of the truth value of P. You can do this by a truth table, and this just says that when P is true, not P is false, and when P is false, not P is true. That's a very easy one. I don't think we need to spend any more time on it. And I think is also pretty easy. Conjunction is an old-fashioned word for P and Q. I just mention it because you may see it in texts, but I won't be using that very often. I'll simply say P and Q. And this statement, P and Q, it's true when both P and Q are true and false otherwise. In other words, in the case P true, Q true, the result for P and Q is true. In every other case, the result for P and Q is false. And I hope you can see that that's exactly what we mean by and in normal speech. If I tell you something and something, then I'm asserting that both of those things are true. Bit of a question you might like to think about, especially if you're interested in the philosophical side of these things. Is the above definition circular? Because I'm defining and, what does my definition say? It says both P and Q are true. So to define and, I've used the word and. So is it circular? If so, how can we fix it? I'll leave that for people to ponder for yourselves. Let's look next at or. And again, an old-fashioned word which I won't use very much. In fact, probably not at all. This is sometimes referred to as a disjunction. The disjunction of P and Q simply means P or Q. And it's true when either P or Q or both is true, false otherwise. So in other words, in this case P is true and Q is true, both of them. In this case P is true, in this case Q is true. In all of those cases the result is true. Only in the last case, where both P and Q are false, do we find that P or Q is also false. That's the truth table. And I hope you can see that this is the inclusive meaning of or. In other words, P or Q, to put it perhaps in more detail, means P is true or Q is true or both. Inclusive or. We can do an exclusive or. We won't have much use for it, but we can do it. The exclusive or, symbolized by P plus in a circle, Q, is true when either P or Q is true but not both, and it's false otherwise. So the only difference between this one and the previous one, the inclusive or, is this row here. So if P is true and Q is true, then if I do P or Q, that's true. But if I do P exclusive or Q, it's false. Every other row of this truth table is the same as the previous one. And as I've foreshadowed, what we want to do is to work out truth values of compound propositions, and we just do it step by step using the results that we've just seen. So let's construct truth tables for not P or Q, and also for not P and not Q. And we'll do it simply, as I said, step by step. So for not P or Q, As in ordinary numerical algebra, the things you do first are those that come in brackets. So first we work out P or Q, then we do not of the result. So first row, for example, P is true, Q is true. P or Q is therefore also true, and not P or Q is false. Second row, P is true, Q is false. P or Q is true, because it's an inclusive OR. If P is true, then P or Q is true, regardless of Q, and therefore not this one is false, and that's our final result in the second row. You can do the third row for yourself, and for the fourth row, P and Q are both false, P or Q is false, and the negation of that is true. So here's our final result. 4 rows of the truth table are marked false, 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 true. For the second one, we work similarly, and perhaps I'll leave it for you to do for yourselves, just to check that, and here is the result. What do you notice about these two things? I hope the answer is not too hard to get. I hope you've realized that the final answer is the same in both cases. False, 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 true for the first one, and false, false, true are the answers for the second one also. And terminology for that is we say that these two propositional forms are logically equivalent. That's to say that they have the same truth values for each possible allocation of truth values to the variables in them. So if P is true, Q is false, then our two propositional forms have the same final result, and the same thing for every other possibility. We denote the logical equivalence of P and Q by writing this here, and I'll read that as P is logically equivalent to Q. As I've mentioned before, we will also be using this symbol here, but that will be different, so please don't mix up these two. I'll introduce that one later on, and I'll also discuss the connection between them. They are related, but they are not identical, and they should not be mixed up. Example of logically equivalent propositional forms. Well, we've just taken these two examples here, these two propositional forms. We've confirmed by means of truth table that they have the same truth values in every possible case, and therefore they are logically equivalent. So not P or Q is logically equivalent to not P and not Q. This is referred to as one of De Morgan's laws. That's a term with which I hope you're familiar from the set theory part of this course, and I hope you'll also recognize the analogy between De Morgan's laws for logic, one of which we've just seen, and De Morgan's laws for set theory. We'll explore that a bit later on, but just something to think about in the meantime. Another example. Let's show that these two propositional forms are logically equivalent. Before we do that formally using the truth table, let's also discuss it informally. Logically equivalent essentially means the statements are different ways of saying the same thing. And I think that you may be convinced of that if I give you the following example. Suppose P is the statement, I had toast for breakfast. Q is the statement, I had tea for breakfast. R is the statement, I had coffee for breakfast. Then the left-hand side there is saying that I had toast and tea or coffee for breakfast. The right-hand side is saying I had toast and tea or toast and coffee. And I think you can see quite clearly those two things are the same. Of course, I've only given you one example, so I'm not claiming proof or anything, but I hope that you would be reasonably convinced by that the left-hand side and right-hand side are just two different ways of saying the same thing. To confirm it formally by using truth tables, we'll build up a truth table for both of them. To save a bit of space, in fact, I'll combine the two truth tables into one. So I've got my values of P, Q, and R here. Notice, seeing we have 3 propositional variables. There are 8 possible combinations of true and false values. So we look at all of them. And I'll find the truth values for both the left-hand side, that was P and Q or R, and the right-hand side, that was P and Q or P and R. Let's just do a couple by way of example. I'll do the third row and perhaps the 5th row, and I'll leave the rest up to you. So here, P is true, Q is false, R is true. Q or R, that's false or true, it's true. P and Q, that's true and false, it's false. P and R. That's true and true. It's true. Left-hand side is P and Q or R. In other words, that's P and Q or R, which is here. It's true or true, and therefore it's true. Similarly, for the right-hand side, that's P and Q. That's this one. Or P and R. That's this one. It's false or true, and the result is true. Let's also do, say, the fifth row by way of example. And the rest you can do for yourselves. So P is false, Q is true, R is false. Q or R is true and true or true. It's true. P and Q is false and true. It's false. P and R is false and true. It's false. Left-hand side. Once again, the left-hand side is P and Q or R. It's false and true, which makes false. And right-hand side, it's P and Q, or P and R, it's false or false, which is false. And you can do all the rest. And then finally, look at those last two columns. The truth values for the left-hand side, truth values for the right-hand side are identical in every one of the 8 cases, and therefore we come to the conclusion that these two statements are logically equivalent. P and Q or R is logically equivalent to P and Q, or P and R. And that's one of the distributive laws, which once again I hope you'll recognize from set theory. So we can show that two statements are logically equivalent by compiling the truth table for each of them. We can also do it on a less formal way by just understanding what the statements mean. How would we show that two statements are not logically equivalent? Next problem. How can we show two propositional forms are not logically equivalent? We could just construct the truth tables and note that the resulting truth values are not always the same. If you think about it, that's rather overkill, because to show they're not equivalent, we only need one example where they have different truth values. And so if we can avoid constructing the whole truth table and just in effect construct one row of it, we're going to save ourselves a lot of time. So show that P and Q and P are not logically equivalent. Another way to do it is to pick specific propositions with which one of them is true, the other one is false. So I'll consider the following propositions. P can be the statement 2 plus 3 equals 5. Q can be the statement 2 times 3 equals 5. Then clearly P is true, Q is false. So P and Q is false, but P is true. So we come up with a statement, a couple of statements there, in which P and Q and P have different truth values, and therefore they are not logically equivalent. Notice again that to say they're logically equivalent means they have the same truth values in all cases. So how do we disprove an all statement? We give you one counterexample. That's all we need. Sometimes we'll come up with statements which are always true. And it's called a tautology, a propositional form that is always true, no matter what the truth values of the propositional variables that occur in it, is called a tautology. A propositional form that's always false is called a contradiction. One which is neither of these, in other words, sometimes true and sometimes false, is called a contingency. Some examples: P or not P is a tautology. P and not P is a contradiction. P and Q is a contingency. And to check this, just either construct the truth tables, which I'll leave up to you, or consider what they mean. So let's do the first there, consider what propositions mean. So P or not P. That's saying that the statement P is either true or false. Now, since a proposition is something which must be either true or false, that is definitely the case. Whatever P is, it must be either true or false, and therefore this statement P or not P is true, regardless whether P itself is true or false. Therefore it's a tautology. Second example, P and not P. So we're saying that P, a single specific statement, is simultaneously true and false. Now that's clearly impossible. So no matter whether P is true or false, this combined statement, P and not P, is got to be false, and it's therefore a contradiction. A couple of comments about these. Any two tautologies are logically equivalent. they have the same truth value in all cases, namely, always true. Similarly, all contradictions are logically equivalent, because given any two contradictions, they have the same truth value in all cases, namely, both false in all cases. Conversely, if a proposition is equivalent to a tautology, then it is itself a tautology.